Okay, so today we're going to discuss using STR loci to track disease genes. Now, we're familiar with these loci for things like paternity and forensics, but the gene tracking is another level of complication entirely. Now, I think I said before that we're going to refer to these loci as A, B, C, and D rather than their proper names, which are things like D1S something, something, something. It just makes it a little easier to look at the numbers. And also the alleles, we're going to just call 1, 2, 3, and 4 instead of the 15, 16, 17, or whatever the actual allele repeat number would be. It just makes the nomenclature a little bit easier to look at. Okay, so in terms of genotyping people for STR loci, we know we can do that easily with PCR, although there are other ways. But when you genotype somebody in one pool, what you get is both alleles, but it doesn't tell you what the arrangement is. So for example, if you're A1, A2, B1, B2, etc., there's different arrangements that are possible for those alleles. So you might have A1, B1, D, etc., all collected on one homolog, and the 2's collected on the other homolog, or you might have a mix and match. So just the genotype itself is not going to give us the information that we need to track a disease locus in a family. We need to know what's where. Okay, so the things to learn here have to do with what's called setting the phase, which is to say we can figure out which allele is associated with what, and we also need to get the idea of informative meioses, which can be useful in tracking disease genes. Okay, so here's an example of a family, and we're just going to look at we're not looking at disease loci here, we're just looking at the A2, B2, or A1, B1 STR genotypes. And just for the sake of argument, what we're going to do is try to identify or try to say for sure what the genotypes are of the children in generation 3, whether there's been a recombination event or not. Because recombination or lack thereof is really crucial to tracking disease genes. So starting with the dad in generation 2, we can see that he is actually something called phase known because we have information from his parents. We know that his genotype is A1, A2, B1, B2, but without looking at the parents, we don't know which A goes with which B. But fortunately, we have parent information, so we can easily determine that. So he is A1, A2, etc., but his father is A2, A2, B2, B2. So we know that he got his A2 and B2 from his dad. So that means his A1, B1 must have come from his mom, and in fact, she has A1, B1 to give to him. So he is phase known. We know what he got, which alleles came together from his parents. So now looking at the kids, we can say what's a parental organization and what's not a parental, which is to say recombinant, whether that A2 and B2 stay together in meiosis in this man or not. So looking at the first child, we can see, and also it helps a lot that his wife is A1, B1, so we only need to look at the alleles from the dad. Everybody's going to be A1, B1 from mom. They make these things easier for us than real life would be. So the first child is non-recombinant because the parental A2, B2 he got from his dad, unrearranged versus what grandpa had. Similarly, the other alleles that he has from dad is A1, B1, and that is also non-recombinant. He had A1, B1 as well from his mother. Okay. So the next child is recombinant because they're A1, B2. They're not A2, B2, they're A1, B2. The next child is non-recombinant also. He is A2, B2. The next one is also non-recombinant, A1, B1. But the next son is A2, B1, which is recombinant. There's been a rearrangement of the parental alleles as a result of meiosis in his father. And lastly, the last daughter is A2, B2 again, that she's got a parental, which is to say non-recombinant, arrangement of alleles of A2, B2 from her father. So we can classify all these children as either recombinant or not recombinant for the A and B loci simply because we know what dad's genotype is and where he got his alleles from. Okay, so it's easy to determine this because we have the information in the pedigree to make this information unambiguous. So setting the phase means that we can just say that, who's recombinant and who's not, because we know what they got from their parents. Okay, so we're looking at dad, okay, And this is just to reiterate what I just said. Looking at him, he has A2B2 from his father, A1B1 from his mother. It could have been the other way around, but the fact that we know what his parents' genotypes are means that we can say for sure that his original arrangement was A2B2 from his dad and A1B1 from his mom. So he's thus phase known, which means that any recombination can be identified as a result of the rearrangement of those alleles. Here's our same pedigree again. Okay, so I'm just going to reiterate what I just said. Because we know what the alleles are, when we know that his alleles are A1B1 and A2B2 are the parentals. The recombinants are A1B2 and A2B1. So if we look at the kids, we can classify them according to whether they have one of the dad's parentals, which is A2B2, or A1B1, or recombinant. So that's a simple matter to do, assuming you know what the original arrangement was. Okay. So we're not always looking at the STR loci and other STR loci. It's more important or more interesting usually to track the STR locus with a disease gene. Now in all the examples we're going to be talking about, except for one, the disease we're tracking is dominant, which helps considerably in this regard. So we're just going to look at these pedigrees and try to decide whether the daughter, the affected daughter in each case, whether her alleles A1, A2, and the disease, if we know enough about them, that we can predict any possible disease in her children. So for example, in pedigree A, the affected daughter is A1, A2. So we look at her parents to try to figure out which allele she got from them along with the disease. Her dad is A1, A1 and has a disease. So clearly she got A1, and her mom is A2, A2 with no disease. So she got A1 and the disease from her father. So this is an informative situation in that the A1 and disease arrangement is known, and this has predictive value as far as her children are concerned. Pedigree B is similar, but it's not informative because dad has A1, A2 and the disease. Mom also has A1, A2 and the disease. And daughter has A1, A2 and the disease. So this is not helpful for us because we don't know. Well, she got the disease from her father, obviously, but we don't know whether she got his A1 or A2 because she could have gotten either one of them from her mother or her father. So that's not a very useful pedigree. Pedigree C is another one where she's homozygous, so she's got A1, A1. She got the A1 and the disease from her father, so we know where she got that, but we don't know. It's not going to be helpful in terms of her children because any children are half and half likely to get the disease, but A1, the A locus, is not going to help us to track that. Okay, pedigree D isn't, so that's not informative. Pedigree D is also informative because, again, the arrangement of alleles. The affected father has A1, A2 in the disease. The unaffected mother has A3, A4 in the disease. So the daughter got the disease and A1 from the dad and the A4 from the mom. Like, that's the only possible arrangement that could have happened. Like, she clearly got A1 in the disease because mom doesn't have it to give, and she got the A4 from her mom because her dad does not have an A4 to give. Okay, so pedigree A is informative. We can figure that out. Pedigree B is not informative because the mother could have gotten either A1 or A2 from the affected father. Pedigree C is not informative. We don't know which A1 goes with the disease. Pedigree 4 is informative. We know that the mom got A1 and the disease from her father, A4, no disease from her mother. So that has predictive value in terms of her children. Okay, so here are some pedigrees that illustrate why it's so useful to have family information. In the pedigree A, we have a woman rather, with a disease, and she has STR alleles A1 and A2. And she has some children, and some of them have the disease and some of them do not. So we can figure out what's what in this pedigree because we have information from her family. She got the A1 and the disease from her affected mother, because mom is A1, A5, and she got her A2 and no disease from her unaffected father. So we not only know what her A1, A2 genotype is, we know which of those A's came with the disease, and that was A1, which she got from her affected mother. Okay, her husband is A3, A4, which simplifies the situations because we don't have extra clashing A1s or 2 walking around here. So in terms of her children, we can classify them as recombinant or non-recombinant because we know the phase. We know that A1 goes with the disease, A2 does not go with the disease. Okay, so if we look at her children, her first child is A1 with the disease, so that's a parental arrangement. In this case, the A2 is no disease, which is expected. We have A1, A4 with the disease, A1, A4 with the disease, A2, A4 without the disease, and now we have the last child is A2, A3 with the disease. So the first children, 1, 2, 3, 4, 5 of them, are all parental, that they have A1 and the disease, or A2 and no disease. The only recombinant in this family is the last child, who has A2 and the disease. So there's been a rearrangement in mom, so that in her case, in this child, the A2 now is linked to the disease locus. Now the next family is the same exact kids and the same exact parents, but without knowing the genotypes of the grandparents, we can't say for sure which A locus goes with the disease or not. We can make a guess because if the A1 is with the disease, then we know that the children all the children except the last one are parental, but we can't say that for sure. So it is extremely important to know which A came from with the disease and which one did not before it can have predictive value in terms of these kids. Okay, so we can represent these in this sort of nomenclature where we write A1 and big D standing for the disease as linked, in this case, by showing the 2 letters underlined. So the underline represents the chromosome just as if it were a fruit fly cross or something. So the underline indicates that those 2 are linked loci and they're linked with those 2 alleles on that particular homolog. Okay, so the other parental, again, is going to be underlined, and that's A2 and little d standing for no disease. So she's phase known what the relationship was between the A and the disease, which A allele and which disease. So that's a standard nomenclature for this. Okay. So pedigree B, again, looking at the children, it appears that A1 is linked to the disease, but we can't say that for sure because mom is not phase known. Okay, here's a pedigree, human pedigree. This one's a sex-linked recessive gene for hemophilia. The gene is located on the X chromosome. So the question here is the affected, the carrier female, 3-3, is she phase known or not? Well, we can look at a lot of evidence that she is in fact phase known. Her brother has a disease, and he carries STR allele 17. Her carrier mother has alleles 15 and 17, and her uncle has allele 17. Her father has allele 20. So we know that she has allele 20 and 17. And we can bet, even without seeing that she's got an affected child, that 17 is the one that's going along with the disease. So yeah, she has an affected son, and he carries allele 17, which is passed to him by his carrier mother. So the obligate carrier woman 3-3 is phase known. The answer is yes. Okay, here's another set of pedigrees which illustrates some other ideas that go with this. Again, we've got a dominant disease segregating, and we're looking at what's happening in the progeny, whether the various meioses are informative, and whether we can get any information from these pedigrees. So looking at the individual, the affected girl in the second generation, she has a disease, and she has STR alleles 12 and 13. So if she's phase known, we can be able to tell from her parents which of those alleles went with the disease. So her affected mother is allele 9 and 12. and her unaffected father is 11 and 13. So we can say that she got the 13 from her unaffected father, and she got allele 12 from her affected mother. Her husband is conveniently 13-13. Okay, so is person 2-1 phase known? Yes, she got the disease and STR allele 12 from her affected mother. Okay, so now we're going to look at pedigree 2, which is very similar but not identical, and we're going to be asked whether individual 2-1 is phase known. So this is similar to the previous pedigree, where she could have gotten allele 9 or 12 from her affected mom, 11 or 13 from her unaffected dad. So the arrangement is pretty unambiguous here. She got the allele 13 from her dad because mom didn't have one to give, and she got the allele 9 from her affected mother along with the disease. So the question is she phase known? Right? Yes, she is phase known because we know what allele she got from where. She got allele 9 and the disease from her affected mother. Okay, looking at pedigree 1 again, we now need to consider the individual 3-1, and we're being asked whether he is or is not recombinant for the disease. Well, mom being phase known, we know that her allele 12 came with the disease, so 12 and the disease are linked, at least to some degree. But looking at the son, he got allele 13 from his dad, because that's the only allele he could have gotten from his dad, and he got allele 12 from his mom, but he didn't get the disease. So he is, in fact, recombinant for the disease, because the allele 12 and the disease allele have been recombined or reassorted from each other during meiosis in the mom. So even though she's phase known, recombination will separate the STR allele from the actual disease gene some of the time, depending on the genetic distance between those two loci. So the person 3-1 is recombinant, non-recombinant, or can't tell. He is recombinant. He does not have the disease, but he does have mom's allele 12, which is associated with her disease. So the alleles are rearranged in him versus in his affected mother. Okay, so now we're going to look at pedigree 2 and ask whether the individual with at the bottom, 3-1, is recombinant or not. So again, we can look at the alleles of the mom, and our situation gets a little more complicated because of alleles from the dad, which are going to confuse our interpretation. So the woman in generation 2 got alleles 9 and 13 plus a disease. Her mom had a 9 and a 12 to give to her. Father's 11 and 13. So she got allele 13 from her dad, allele 9 from her mom, along with the disease. So those two are associated in the mom. She's phase known. If we look at the child, he's 9-13 and no disease. So the question is he recombinant or not? Well, his dad messes up this analysis because mom has 9 and 13, dad has 9 and 13. So the kid could have gotten the 9 from either the mom or the dad, could have gotten the 13 from either the mom or the dad. So the question about whether he's recombinant or not, you just can't tell from this information. Right? He could be recombinant, he could not be recombinant, but because of the ambiguity having to do with what alleles are coming from which parent, you can't answer that question. Right? The problem is he could have gotten either allele, 9 or 13, from his affected parent, and that's because the other parent has the same alleles. Okay, so comment. Remember, the STR locus that's being tracked is not the actual disease gene. It's something nearby. Now, sometimes nearby is actually within the gene itself, and that will cause the fact that you will have very, very little recombination between the two. But sometimes they're a little bit further away, so that recombination can happen, which can cause problems in interpreting problems in using this information diagnostically. If it's too far, then the STR recombination can confuse the interpretation of whether the child did or did not, will or will not get the disease. Okay, here we're considering two different STR loci, A and B, and also a dominant disease gene. And we're being asked to interpret this in terms of recombination or lack thereof between the two STR loci and the disease itself. And I'm not going to do the whole worksheet right now, but I will answer some of it, at least tell you enough about it to be able to do the rest yourself. Okay, so the question is, which alleles of STR A and B did the affected man inherit from his unaffected father? So here you have to look at the genotypes of the people and see if you've got any unambiguous interpretation of these. And it turns out you do. You answer, if you look at it, he got A3 and B4 from his unaffected father. Right? Which did he get from his affected mother, A2B3 or A2B4? Okay, he got A2 and B3 from his affected mother. And you can look at the genotypes of the various people and see that this is the only way it could work out, that he got one allele from each of those loci from each of the parents, as well as a disease from the affected mother. So now that we know what the allelic arrangements are in the parentals, we can classify all the children as whether they're recombinant between the A locus, the B locus, and the disease. So the A locus is pretty simple. We know what the parentals are. We know that A2 is the one that came with the disease because that's where Dad got the disease A2 along with the disease from his affected mother. So A2 with the disease is a parental. A3 without the disease is also a parental because he got the A3 from his unaffected father. So the first child, A2, disease, parental. Second child, A3, no disease, parental. Third child, A3, no disease, parental. Fourth child, A2, disease, parental. Next child, A2, disease, parental. A3, no disease, parental. A3, no disease, parental. So in this case, A3, or the A locus, appears to be well linked or tightly linked to the disease locus because all the children are parental. There's been no recombination between the A locus and the disease in any of these, in meiosis in the father for any of these children. Okay, the B's are going to be a little more complicated because they're going to have some recombinants here. Okay, so originally B3 was the one that came with the disease in Dad, and in fact the first daughter has B3 and the disease. So that's a parental configuration. There's been no rearrangement. The next child, however, is B3, no disease. So that's a recombinant because the kid got B3 but no disease. The next kid is B4, no disease. Now that was the original arrangement, so that is also a parental. But the next child is B4 with the disease. So that's a recombinant because it rearranged the original alleles. The next one's B4 with the disease. That's also a recombinant. And then we have B3, no disease. Well, that's also a recombinant because originally it came with B3. And the last one is A3, B4, well, B4, no disease. And so that is a parental. So the trick here is to go through them one at a time, decide what's parental, what's recombinant, and just classify each of the progeny in that way. Okay, the last thing, which I'll leave for you to do, is to look at the A and B loci separately and ask whether the A and the B are linked to each other. Okay, we just looked at A2 linkage to the disease and B4, but importantly, you should be able to look at the A and B separately. Now, we've already shown that A is tightly linked to this locus, and B is unlinked from it, implying that A and B are unlinked from each other. But you should be able to go through the data and show that that's really the case. Okay, so A appears to be linked, B does not appear to be linked, etc. Okay, so important to remember that we're not looking at the actual disease gene most of the time. And summary about how useful these things are depends really on how far apart the markers are and the probability of recombination occurring between them. Clearly, a very tightly linked marker is much more useful for diagnostic purposes.